Hi, good evening. Can you hear me? Am I audible? Vinay, could you please confirm that I am audible?
Yes, sir.
Okay,
Yes, sir, you're audible.
thank you. Okay, we'll start. Then it's already 5 past 6. So this is the last session of the course Power Electronics, Fundamentals of Power Electronics, which is instructed by Professor A. Lumanand from ISC Bangalore. So we have as of now covered all the lectures in our sessions. Mm, we'll just quickly go through what all we have studied till now in this course. Mostly any power electronics course or the whole power electronics stream can be divided into 3 parts. One part is device, other part, its device is a component part. Mostly okay, let me put it in this fashion, that majorly 2 parts. One is the power circuit and other part is the control circuit. Now power circuit, mostly we talk about um, devices, the converters, the circuits themselves. Then we talk about magnetic circuit designs, and in some courses or maybe in some advanced research courses people talk about capacitors. I'm not talking about capacitor design but other issues about capacitors mostly. On the other hand, the control circuit part, we have the controller itself, and what we have is the gate driver. So these two, so this all these things are covered here, have been covered in this course. Now if we look at the converters that we have studied, very briefly, AC-DC converters have been discussed. DC-DC converters have been discussed in good details, I would say. Both isolated and non-isolated type of converters we have studied, and DC-AC, that is inverters, have been discussed in the last lecture only. On the other hand, there is another type of converters, that is AC-AC converter, cycloconverters, but uh, cycloconverters are not that much used nowadays. If you have to have AC-AC conversion, what people do is they convert AC to DC, then convert that DC again to AC using an inverter. Inverter control is much more easier and sophisticated, elegant, I would say, and the output is better in terms of quality when compared to a cycloconverter. This is the most popular scheme used almost everywhere nowadays, where you need AC to AC conversion. So you have AC to AC. Other than this, rectifier controlled rectifiers are not discussed in this course. Only I think uncontrolled rectifier single phase was discussed, single phase and three phase, and DC and these converters were discussed. Alright, so since this is a revision class, I will mostly take doubts from you from the course or anything in general from power electronics, and then I will discuss two problems today. Yes, go ahead. Your doubts. You are planning to appear for the exam, certification exam?
Yes, sir.
You are. Okay.
Sir, about the exam,
Hmm.
so what about like, just can you brief about the pattern, how it will be?
And no, I think you have to write to the course TS. I am not a course T exactly.
Okay.
They can tell you. My job is only to clear your doubts
Okay, sir.
about, I mean, technical doubts. Okay.
Sir,
Yep.
sir, can we discuss about that magnetics in push pull, full bridge or half bridge?
Push pull. Okay. Let me just look into where is it. We see we had push pull here. Magnetics means, so which aspect do you want to discuss?
This transformer part alone.
Okay.
The converter part doesn't need.
Okay, we will discuss with this circuit. Okay, with respect to this. Right. So, so if I call this switch as S1 and if I call this switch as S2, now we know that the switching pattern is like this. Say, mm, if this is the full time period T and this is the half time period T by 2, then S1 is switched like this and S2 is switched like this. These two durations are same. These two durations are same. S2. Now we look at what happens when we turn on S1.
Okay.
Now, so if you see, uh, when you're turning on S1 means when you're closing S1, this current flows like this. So basically what we have is we have the voltage. If I call this VDC, we have the voltage VDC here. Okay, let me not write VDC, let me write this as V1, write this as V2. So when S1 is closed, V1 is VDC. So if I draw V1 here, so V1 is VDC. Now at this moment what happens is we are first considering this to be an ideal transformer. Okay, ideal transformer means it draws zero magnetizing current. Now if it draws zero magnetizing current, what will happen? So if I draw this current, do we say I write it I in, then you see if this is V1 and magnetizing current is 0, if I call say this as N1, N1, N2, N2. Now if this is V1, then V3 is N2 by N1 V1, that is VDC. Write it V1. So N2 is so V3 is positive when S1 is closed, then this is N2 by N1 VDC, which is positive. So D1 will conduct. Okay, now if you see here, so this voltage is how much? V3 by V1 times VDC, which is a DC voltage, and this voltage is V out, which is again another DC voltage. So you are applying a DC voltage across an inductor. So what will happen? The current will rise linearly. So if the current rises linearly, if I draw the inductor current IL, the current increases like this. Okay. So if the current is increasing like this, then what is happening? This is the exact current that is flowing through the transformer winding. Now this current will be reflected here. This current will be reflected here, so it will come like this. So if I look at I in will also look like this with proper scaling. Just a minute. Yes, with proper scaling. So like this. Now at this moment there is no switch turned on. There is no switch turned on in the circuit, right? So what is happening is that there is no current in the primary, and the current IL that was flowing like this. So IL, if I draw there, I can also draw IL here always. So that gets divided in these two diodes, in these two transformer paths. Now you see here for this winding, IL is going out of the dot terminal, and in this case current is going in the dot terminal. Now their number of turns are same, the current flowing through them are the same, only thing is that the direction is opposite. So the flux created or the MMF created by these two windings are the same in magnitude and opposite in direction, so they will not create any net flux in the core, right? And since this is an ideal transformer, it was not it was not carrying any flux at all when this S1 was closed also, right? So if you look at in is 0 here, sorry, in is 0 and IL drops like this. So this is the thing. Now now if you have to look at the transformer flux, how the flux looks like, obviously we cannot do it here because we are talking about ideal transformer. If you look at practical transformer, how would the flux look like? Right. Now for a practical transformer, what we have to do is we have to consider a magnetizing inductance. So let us say the magnetizing inductance is here. We consider the magnetizing inductance here on. We discussed this, that we can consider it anywhere and can analyze the circuit. Now this is VDC, this is S1, this is S2. Now what is happening is, if we look at the core, when you close S1, then apart from the load component of the current which was being drawn previously, like this inductor current is increasing So this current is also increasing like this. That thing happens. At the same time, another increasing current flows through this magnetizing winding, and this also looks like this, linearly increasing, because it is an inductor and you are giving DC voltage across an inductor, right? Now what happens is, you are so okay, let me draw the current direction also. When S1 was closed, current was flowing in this direction in the magnetizing winding. Now when you open S1, a times come, say during this time, when no switch in the circuit is closed. At the time, what happens, in the secondary side, the inductor current is divided into both the windings and they cancel each other's flux. That is fine. But what happens here in the primary? The In the primary, if you make the circuit like this, the switches will simply fail. Why? Because the magnetizing current was flowing before this one was opened, and the energy, the stored energy, has to go somewhere. Since it has no path to go, it will quickly dissipate across the switches, and the switches will fail. So in a practical um, push pull converter, what you have to have is a diode. So your diodes must be put like this. It is like this. So just a minute. You open this. Yes, it should be like this only. Let me check. Yes, now what is happening when you open this switch? Then this must be given a way to flow. How will it flow? See, obviously, if I draw the diodes, write the diodes at D1 and D2, the current that was flowing through the magnetizing winding cannot flow through D1. So what it will try is, it will try to rotate like this along this loop. It will rotate along this loop, and definitely the current will be decreasing. So now if I draw, so if this was my V1, so V1 is Lm dim by dt, which is negative, and this was my V2. Now since V1 is negative, and since we have N1 equals N2, we have V1 equals V2, which is negative. Am I drawing the diodes opposite? Yes, this diode I drew opposite. This diode cannot be in this direction, otherwise it will always turn on the voltage source like this. Now it is fine. See, it cannot be the other way around, otherwise the voltage source will always keep on supplying the winding. It's like this. So what is happening when I'm opening the switch S1, then V2 becomes negative because of this dropping current. Now V2 becomes negative means, you see the actual polarity. See, with this polarity of V2, it is negative. That means the actual polarity is like, sorry, actual polarity is like this. So this can make the current flow like this. So basically what is happening, when you are closing the switch S1, some flux is flowing through the transformer core, that is, some energy is stored in the magnetizing winding. When you are opening S1, that energy is given back to the source. How is it given back to the source? Through the other winding. When S1 was opened, sorry, when S1 was closed, this winding 1 was excited, but when it is opened, through winding 2, the stored energy goes back to the source. Is it understandable?
Yes, sir. But how it returns back to the inductance Lm?
Okay, let me draw it clearly once more. So if this is the circuitry, see, all these things are wound on the same core, okay, same transformer core. So they all are coupled, magnetically coupled. So they all experience the same flux.
Yes. Okay.
All of them experience the same flux. Flux linkages might be different depending on the number of turns, but they look at the same flux. Right, so if this is V1 and if this was the magnetizing inductance, when S1 was closed, the magnetizing current was in this way. Right, so if it is in this way, I can write this equation.
Yes.
Right,
Yes.
now it is demagnetizing. During the period when both the switches are off, the magnetizing energy, the stored energy is going back. So definitely the magnetizing current is reducing, demagnetizing. That means this Im must be reducing at that time. That means V1 must be negative. Right. Now depending on the dot convention, if I write V1 and V2 in this fashion, then I can say V1 equals V2. See, I am writing in lowercase, means I am saying instantaneously they are equal. That means their polarity is also equal. Okay, so now what is happening? So if V1 is negative, V2 is also negative. V1 is negative, so V2 is also negative. And if V2 is negative, that means the actual polarity of V2 is like this. Right, so this can forward bias the diode and make the current flow like this. So what is happening in the equivalent circuit? In equivalent circuit, the magnetizing current is flowing like this, and it is reducing, and this current is reflected in this winding, which is flowing in this fashion. So the stored energy is going back to the source. Now if we draw this circuit once again and look at what happens when S2 is closed. So this was the circuit. All of them are connected. This is the magnetizing winding. These are the two diodes. Now S2 is closed. S2 is closed. Now what is happening? If S2 is closed, then I wrote the voltages V1 and V2 in this fashion, that I will not change. Sorry. Then V2 is minus VDC. Right, so as V1. So if V1 is negative, that means this voltage is also negative. That means this is forcing a current in this direction. In the magnetizing inductance. Now if you compare,
V1 is V1 equal to VDC.
V1 is minus VDC. See, S2 is closed now. If S2 is closed, what is V2?
V2 is minus VDC.
Minus VDC. And V2 is equal to V1 depending on the dot convention. The way I have given the dot convention, based on that I have to write V2 is equal to V1.
Okay.
So V1 is minus VDC. So if V1 is minus VDC, that means it is now forcing the current in the magnetizing inductors in this fashion. So Previously it was downwards, now it is upward. So if you look at the magnetizing current of this push pull converter, it will be like this. It will be like this. So it will increase, then reduce to 0, then again, say if I say the duration is 50%, it will look like this, or if it is less than 50%, it will look like this. Then again increase on the other round, on the other side, decrease to 0 in this way. So this will be the magnetizing current or the flux in the transformer winding, in the transformer core.
Sir, here also the flux in the core is only because of magnetizing winding. The other fluxes cancel.
Yes, that thing still holds. That there are currents in the other windings, but that get their opposite, and the number of turns is same, so they cancel each other's flux. So at the end, how much flux is flowing through the transformer core depends on the magnetizing inductance and the supply voltage and duty ratio, obviously. So that does not depend on the load. So keeping everything same, if you change only the load, flux will not change. Flux in the core will remain the same, like any transformer, any power transformer.
Here at any instant, at least one winding will be carrying the current.
Yes. And the diode current of this converter is also interesting. I hope you understood when we discussed.
Yeah, we draw on the place. That it will become a half and then it
Yes,
decrease.
so for during this on time, sorry, during this on time, it will follow inductor current. Drawing it wrong, one second. It will follow the inductor current. Then when it is off, it will become half because it is sharing with other diode. And then stop. And before this, it was sharing. So reducing from somewhere half of this value like this. So this black one is the diode current.
Sir,
Yeah.
In the suppose we have a winding in series with the switch. Suppose if you take a forward converter, in that if we switch off uh, on the primary side, if we switch off the Q, then there will be usually we consider the leakage inductance to be 0, and we say that the inductor voltage across the inductor reverses when we switch off this switch. Uh, but we will just put reverse the same polarity of the source voltage, the same value of the source voltage we will put, and we will reverse the polarity at the instant of switching off.
Just a minute. Yeah, tell me, what is the question?
No, sir. At the instant of switching off of this switch, uh, we will put we will just change the polarity of the primary winding, that is the magnetizing winding, and we'll put the same source voltage at that point.
We do not put, it happens.
Yes. Okay.
And not the
Sir,
same source voltage. That depends on the turns ratio that you are keeping. with the reset winding. There is a reset winding, no?
Okay. Uh,
Today on control system, no. Last class was on control system. But you can ask if you have questions. Yes, go ahead. So basically, when you turn off the switch, when you open the switch, we have seen how this diode starts conducting, how and why the diode
yes.
D3 starts conducting. So if D3 starts conducting, then what do you have? You have, say if I write V3 in this fashion, then you have V3 is minus V in, and since I have put dot plus, and here if I also put V1, then this becomes equal to V1. Sorry, V in. Now V1 is N1 by N3 times V3, that is minus of N1 by N3 times V in.
Okay. Sir, here that there will be a spike in this V1 as soon as we open the switch.
No,
That is because
if you do not consider leakage, then there will not be any spike.
okay. Sir, how can you explain this statement? How by considering leakage there will be a spike?
Okay, so if you want to consider leakage, let me now then draw the circuit. This is the leakage inductance, and this is the magnetizing inductance.
Yes.
Okay, now the terminals that you can access are this and this. Inside this you cannot access anything, right? Everything is lumped parameters here,
Okay.
right? Now if you just want the answer in a statement, then the statement is uh, when you're turning off the switch,
Okay.
then the energy stored in the magnetizing inductance Lm, that has a path to flow, uh, how to say, that is a path to flow, or since we can say that Lm is coupled, magnetically coupled to the third winding,
Yes.
reset
Yes.
winding, the energy can flow to it. But the leakage winding, the leakage inductance current, that has no path to flow. As soon as you open, the current through it breaks, and it was carrying the full load current plus magnetizing inductance current. That current breaks, and it has no path to flow unless you provide a snubber.
Okay.
It has no path to flow. So then the only thing that can happen is the stored current, stored energy in leakage inductance will drop across the switch, will be dissipated in the switch. Or in other words, since you are interrupting the current, then the voltage across the leakage inductance, which is given by LL, sorry, L, yes, di by dt, this voltage will come as a spike across the switch. So ideally, when turning on the turning off the switch, we expect a voltage like this, but we will get to see a voltage like this, something like this.
So this is the spike waveform is the more practical one.
Yes, and you have to use a snubber if you want to avoid that. Derivative control. What is derivative control? PID derivative control, is it covered somewhere in the course? I don't think so. I mean, I don't have any idea about it. I have to study. Only PI was covered in the course. Is this covered somewhere in the course? This PID derivative control or something? Okay, go ahead. Other questions? PNP transistor working? Device physics, you need not, that is not covered, and you need not know also much to study this power electronics. All I can say is just consider it as a switch. I used to say these things a lot at the beginning of the course. Device physics, I also don't remember, it is not required anywhere in power electronics at least. So this is the PNP transistor. PNP transistor, the thing is, say if you have the DC voltage, say here, and if you have the load here, and if this is the ground, and say you are deriving this from somewhere, some other ground, wait, this has to be with respect to this. So yes, so when this is high, the switch is open, like that is opposite. When this pulse is high, the switch is considered open, and when this pulse is low, the switch is considered as a switch Q is considered closed. That's all you need to know. Inside physics, if you want to know, you have to read electronics books, Cedra Smith and all. But that is not required in power electronics converters at least. Okay, if not anything else, I'm planning to discuss this today.
Sir,
Hmm.
sir, after this course, if we want to go into this industry, some electronics industry, which are the, how can we go into, which are the skills that we want to develop further? To, we don't know which companies available in this domain also.
Out of this course means your graduation is over,
No, no.
so you have to means why do you want to go in internship or job or what?
Yes, sir. Both internship and for a job. Uh,
See,
If I want to start my career in this electronics industry.
industries would want you to have practical knowledge. Okay. So practical knowledge, if I talk about very basic things that you must have in power electronics is, say, PCB, right? Even before PCB that comes is this. Then mm, say testing, say your experience in magnetics, how you design and wind magnetics. These are the direct hands-on experience. One more things that you will need is design of circuits, simulations. Mm, I would say that if you want to join industry for in the power industry, then try to take your BTech dissertation on power electronics, BTech project,
Okay.
and try to make some circuits that you will design and fabricate. They
Sir,
seek
which
for hmm,
yes, sir, you were about to say something.
no, they seek for hands-on experience in power electronics.
Which are the softwares which we, if we know, they will prefer us?
See, for simulation, the most generic software is SPICE. Okay, SPICE is a specific kind or a specific way of circuit simulation. Now there are several softwares. I will mm, name one free software. This is LT Spice. This you can download and use for simulation. This is for very how to say, very practical issues you will get to see if you start simulating in Spice, because the device models, Spice models and all are used here, and all kind of non-linearities, non-idealities are considered. And for teaching purpose, I prefer to use another software uh, which is called Sequel. Is another free software. This was developed at IIT Bombay itself. This will not give you so much practical insight, but will give you about the a lot of knowledge about the mm, working of the circuits. And now, if you yourself incorporate non-idealities and non-idealities in the circuit, then you also get to see the behavior of the circuit, what happens in non-ideal cases. This is mostly for simulation. For PCB, I think no, not FreeCAD. KiCad is one open source software where you can design PCB, and there are other softwares which are paid softwares. We should not name though, but they are popular actually. The most popular is Altium. This is something that you can add as a skill in your CV if you are going to join one PCB on power electronics industry. If you know Altium, that's a great sort of skill. Other softwares are used, Eagle, that is from Autodesk, the same company that makes AutoCAD. There is another software. These are all paid, and KiCad is free.
Yeah, they are using KiCad in this course, sir. Yeah.
Hmm.
Uh,
This is the most used software. Professionals use this.
Sir, if
Hmm.
we want to design, do the programming on PWM, that control
Hmm.
of
Hmm.
electronics, what we should do, how we should, if we want to improve our knowledge on that.
See, first thing that depends on that depends is where are you going to. write your code, means which controller you are going to use. Okay, the most popular or what everyone knows about is Arduino. Okay, so you can start writing codes in Arduino. You can write codes in C. Arduino boards are not very expensive also. I think for 500 rupees you will get Arduino Uno. That is not the original one that comes from Italy, but that thing works. I used to use some time back, but this is not a very high frequency, so you can start your work with it. You can get to see how things work, how to write a code that runs continuously. Those things you can start with Arduino. Then if you want to look at actual processors that people use are the, say, TMS 320 series microcontrollers used. Like one I used to use, that is TMS 320 F 28379D, something like this. Do not take this, doesn't matter, they keep on upgrading. So TMS 320 series DSPs, they say, that is made by Texas Instruments. So these are DSP, very high speed DSP. You can go for very high switching frequency. Now there are several ways of coding this. If you want a very easy way of coding, you can simply use Simulink. Like you make uh, make the block diagram of your control circuit what you want, and then dump the thing in Simulink. What MATLAB will do is make the code of it, then dump it to this controller. Then you can control your converter using that. Or else what you can do is, means since this is easy, it is less flexible and less efficient also. Another one, I will not say it is difficult, but more difficult than Simulink, which is directly writing the code in C using Code Composer Studio, CCS. With this, you can directly write your code in C and then dump it to the Arduino. See, the thing is, I think you guys know about this. Say if this is the processor, no, the processor understands only one language, the hex. That is the assembly language it can understand, right? So the most efficient way of coding is coding in hex, right? Now this is the lowest level language, assembly language. Now above this comes, see, in computer science there are several things. I do not know all of them, I'm not discussing them also. I'm talking in terms of this controller programming. Mostly people write in C. Okay, so you go up, means your work is easier, but the thing is less efficient, more flexible but less efficient, and your work is easier. You go up, you can write with Simulink. Okay, easiest, anyone can do. But say one problem that I faced in Simulink is I was not able to get the proper frequency that I required from the controller board. Not only that, I was not able to get a dual core coding of the controller board. With the C language you can do. So people do not generally go this down, but this is a good optimum way of programming. Okay, this is very widely used. One more thing, see, again I am going in towards more and more expensive solutions. This is FPGA, fully programmable gate array. I have not used it ever, but you know about gate arrays. Gate arrays are something like this. Say you have several gates in this fashion. and array. Okay, so something like this, maybe in this way they are put, and there are switches. Sorry, so between these two there is a switch, between these two there is a switch, there is a switch, in this fashion. So when you are coding this, basically you are coding these switches, which one to turn on, which one to turn off, in this fashion. What happens is, since you have so many gates, this whole thing operates in parallel. It is a hardware. See, when you are writing a code to to program TMS 320, maybe, or maybe, if I think you have already studied these controllers, uh, 8085, right?
Yes, sir. That microcontroller we have studied.
Microprocessor. This is a microcontroller. Is a 51. So these things are serial processors. There is one address pointer or something, I forgot the terms, that goes one by one and keeps executing the comments that you have given. So there is a delay, potential delay. If TMS 320 and all, what they do is they make the process so fast that it looks like a parallel processing. But FPGA is a real parallel processor. You have hardware, you have a large chip, and this is the FPGA chip. There are several companies, Altera, Cyclone, and all. They make, and you program this, but you cannot simply buy the chip directly from the market and use it. You have to make a development board. In this fashion, in this regard, our IISc Bangalore has done an excellent job. They have developed very high quality FPGA development boards. They sell it. I don't know whether they sell it even now. And not only that, they have made excellent manuals also for that. So anyone can simply read the manual and learn and use.
Oh,
Okay, IISc Bangalore, they distribute things for free. That's a very good thing. Yes, the board you have to buy the hardware, but manuals and all they distribute for free. This is one thing. There is even more, um, what to say,
compared to, so
compared to.
those boards compared to the market, it will be lesser price only for
Yes,
us, right?
yes, I think so.
Can you tell how to approach that one, sir? Is there any way now? Even though it is older,
Um,
how?
I'm not sure who developed the board. The name is coming to my mind, but I one student was there. No, I cannot remember. I knew his name. He had a company.
Oh,
I cannot remember his name. He was making this on IISc alumni. But if you want to try your hand, I would recommend you to go with this one.
ah,
You can directly buy it from online, or there is another way of doing it, that is directly buying it from Texas Instruments, and if your university has a duty exemption certificate, produce it, and you will get it at cheaper price compared to the websites. But that's a long process. We bought it some 3 4 in bulk, but if you don't have that much time, then you can simply buy it from internet, from Digitech and other websites are there. Okay, and one last thing, these are very expensive. Things like Opal RT, again, these are paid things. Opal RT is one, and there was another.
this is the hardware, sir.
This is hardware. They are used in HIL, hardware in loops. I cannot remember what happened to me. Opal RT, and what was the other one? DSpace. So these things are nothing but very expensive. They are nothing but several DSPs inside them, several processors inside them. The processors themselves are fast and several processors working in parallel. So overall the system is very fast and it is extremely easy to control these things. Means if you have one Opal RT, simply connect it to your laptop and you make a Simulink code, dump it, and your control circuit is ready. Generally people use all these things for research purpose. You understand? No, in research we need flexibility. Okay. So when even as a company, if you are when you are doing research at the development stage, you need flexibility. So that this
Yes.
Opal-RT and all that gives you the flexibility. So that's why it is expensive. Now once you are sure about your control circuit that okay, this is what we are going to finally produce in our final product, then you finally make one ASIC maybe or a PCB, whatever you want. Then you do not have any flexibility but a compact thing, exactly what you want you have. So these things are the controllers that we use mostly in research. There are people, I have seen my friends sometimes using PIC, another controller. They would program it and burn the controller with a PIC kit and then run the circuits with it. Thing is, if you can learn these things and code them in assembly language, that is actually the whole process is very enjoyable. I don't know if you have done this kind of experiments in your BTech, where we had to do this. That so we were given some task that write a program to do these things in 8085. Okay, so we used to write the program in assembly first. Then there was a table that will give you the relation between the assembly mnemonics to the hex. Then we will translate it to hex looking at the table, then directly feed the hex numbers to a trainer kit using 1 2 3 4 ABCD and all. Then we run the controller. There's a whole development board, the whole training kit. So basically it's the whole thing. Since the assembly is the lowest level of language, you get to see how it exactly goes. There is no hidden loops, there is no hidden nothing. What exactly happens in front of your eyes. So that is the most efficient coding. So you can start with it for learning. Later on you can shift to TMS 320. I would suggest you to stay at TMS 320 from the point of view of flexibility and price. This is an optimum solution. Ease of use and price.
This Code Composer Studio program we can learn the online tutorials are there, sir, to learn this Code
Online
Composer.
tutorials are difficult. I don't know. Try to find out if any IITs are
Okay.
what to say, arranging. Like in our university, Professor Mukul Chandorkar, he teaches this. Because I remember I tried to learn. You can like if you like Texas Instrument, they release everything, their assembly language things and all. You have to sit and learn. No such lectures I do not think is there.
Okay. So programming is TMS.
Hmm. Okay. We'll look at this question later. This is the last day's leftover question. Let us look at this question. I was talking about this, that you should be able to solve any circuit, any DC-DC converter with the knowledge that we have gained in this course. Okay. So this is one unknown DC-DC converter. The circuit is given, everything is ideal, and the switching pattern is given. Okay, we will see whether we can analyze this. So our objective is to find out the output voltages. So you can see this is a multi-port converter. It has two outputs. One is here, VB, and one is here, VDC. We will try to find out the relation between these output voltages with the input voltage Vin. So we have the, let me draw it once again, otherwise the circle will go away. So there are three switches, and the whole duty ratio is divided into, the whole time period is divided into 3 hubs. Okay, I'm not drawing this once again, I'm just writing. So for the first 1/3, S1, S2 are closed. For the second 1/3, S1, S3 are closed. For the third 1/3, S2 and S3 are closed. Okay, now what I said, our first step would be to look at the inductor voltage. Why? Because at the end we will apply the zero voltage, sorry, the volt second balance in the inductor. So let us take this as VL1, this as VL2, right? Now let us come to the first 1/3 this time. So
Yeah.
we will draw VL1, sorry, we will draw VL1 and we will draw VL2. Okay, let us see. Let me just remove this. Since the integer will be negative also, I will give some more space. Yeah. So S1 and S2 are closed. Let us draw the circuit once in. Although it is not needed, maybe this much spoon fitting is not needed, but we will still try to do it in step-by-step fashion so that we can, or you can, later solve complicated circuits. So S1, S2 is closed, so it is like this, circuit is like this.
So Vin.
So we have our VB here, S3 is open, so this circuit is separated out. So this is VDC, VB, VDC. So what is VL1? Sorry, VL1 is simply VB in. So we'll write VL1 as V in. What happened? This is V in. And what about VL2? VL2 was like this. So VL2 is minus VBB. VB minus VB.
Yes.
So minus VB. Okay. Now comes the next part. So this is the first part. Now we look at the second part. Second part, what is happening? S1 and S3 are closed. S1, S3 are closed. So
VLM is
this is
Vin
directly, just a minute. This is directly connected to the output. We have our VL1 here. S3 is closed, S1 is closed, so it is like this, right?
Yes.
So we have VB, we have V output. So what is V4? V4 is V in minus V naught. Now a question comes is, we know it is V in minus V naught, but we are trying to draw the waveform. We can draw it later also, we can simply keep a note, but I think it will be a boost kind of converter. Why do I think so? Because you see, like a boost converter, we short circuit the inductor, so I mean we keep this kind of loop in one cycle where the inductor is charged from the source, then we give it the power to the output. So it looks like V output will be more than V in.
But this IL1 is not discharging now.
It has to. In boost converter, what happens? During this
Yeah,
time, it
discharge.
increases.
But here, since S1, S3 are on at the next cycle, VL1 I think doesn't have the path, so it will have the path
Hmm.
to the output
Okay,
capacity.
let us do one thing. Let us not draw the waveform right now. Okay, let us not draw the waveform right now. Let us just keep a note. So during the first half, VL1 is V in, right?
Yes.
First one third. Second one third, VL1 is V in minus V naught. Third time, what is happening? S2 and S3 are closed. So it is like this. S3 is closed, so it is like this. And S2, so this is open. So we have a circuit like here. This is our VL2, this is our VL1. So what is VL1 here? Again, sorry, this is L1. Again, it is V in minus V naught, right?
Yeah.
Let us keep a note of VL2 also. So here VL2 was minus VB. Here VL2 is, this is our VL2. So what was this? V out minus VB. And the third case, VL2 is minus VB, right?
Yes.
Yes, minus VB. So we have this. So we do not know waveform. We will look at waveforms later. But what we can do is, see, the switches are on for same time, T by 3, T by 3. So what we can do is, we can now apply volt second valence. So for the inductor L1, we can write T by 3 times V in plus T by 3 times V in minus V naught plus T by 3 times V in minus V naught. So I'll just make a 2 here equals 0. So what we have is T by 3 gets cancelled out. We have 3 V in equals 2 V naught. What happened here? This thing is a bug of one note. Is it correct? V in is equals to V naught. 3 V in equals to V naught. So now we have a relation between hey, what is V naught? Oh, I was writing VDC as V naught everywhere. So 3 V in is 2 VDC. So VDC is 3 by 2 V in. See what I said? It will be more than V in. It looks like a boost converter. That's why I guessed it will be. Okay, so for L2 we will see, so the times are same. Okay, I'm not writing again T3 times, I'm just adding them. Minus VB plus V naught minus VB minus VB equals 0. Okay, so V naught is VDC basically. It is V. So
VDC by
DC.
3.
So VDC. So VDC by 3. Again, VDC is 3 by 2 V in, so half V in, right? Yeah. So we have relation between V in. So this is our
Is output and input, and then this
two
VB and VC.
outputs and input. Now, if we want to draw the waveforms, we can. So V in was there. For VL1 during the second half, it is V in minus VD, and V in is greater than, sorry, V in is smaller than VD, so it has to be negative. So this voltage has to be negative, and it was the same voltage throughout. So this is the voltage in VL1. So I am drawing the current also. This current will be something like this. And for VL2, it was minus VB here and minus VB there. So, sorry. So, like this. So this must be a positive voltage. Just look at it once. VDC minus VB. So VDC is 3 times VB. So VDC minus VB is positive. So this. So if you draw the current in VL2, sorry, in the inductor 2, it will be like this. It will increase for this time. It will decrease like this. Clear?
Yeah, it will come to the bottom line now. The decrease in current.
Look at it clearly, carefully. See what is happening. This is one complete period. Let me draw one more period. Minus VB plus something, this. Again comes the minus VB. So if I draw one more period, minus VB comes here also, no? This thing is repeated. This is repeated. So this whole time is when the current falls.
Okay.
You see? So this half is nothing but repetition of this.
So still the ripple frequency and the voltage frequency remains same.
Yes. Ripple frequency, voltage frequency must remain same in an inductor.
Yeah.
You have to see whether what is the relation between switching frequency and ripple frequency. That is also same.
So
All right.
this can be used for one DC source can be used for supplying two loads.
This kind of converters are called multi-port converters. Multi-port. Nowadays, multi-port machines are also gaining attention. There will be several electrical and mechanical outputs. Generally, we have one electrical and one mechanical output. Multi-port machines may have two mechanical outputs, three mechanical outputs.
Three mechanical. It will have three shafts, sir.
No, one shaft. Yes, you are right. Three shafts. Three shafts. You are right. Generally, what people do, but there can be exceptions also. People might be doing depending on what they need. say if this is one shaft, the machine members are resting on it. Say if this is the stator, okay, then maybe just above the stator there is one rotor. I'm drawing the cross section, you can understand, right?
Yes, sir. Vertical cross section.
Yes. So this is one rotor. See, this rotor is supported on it, on the shaft, using ball bearings. Okay. Then there may be another rotor. And it is supported here using ball bearings. There can be another like this. And this shaft is supported somewhere on the ground. So you see the shaft is not rotating, but these rotors are rotating. And you can tap your mechanical energy from here. There can be, so this is an example where you have multiple mechanical ports. There are machines with multiple electrical ports like your DFIGs, doubly fed induction generators. These are wound field induction generators or induction machines where you have electrical connection on both the stator and rotor. Stator you always have, rotor instead of shorting them you have another converter that is used in wind power generation, very popularly used. So these are examples of multi-port machines. You can have multiple electrical and mechanical ports.
Where these having applications where this
This I told that wind power this is used,
DFIG.
very popularly used. And this kind of things, if you look at this multi-port, one example I know of is say if you need, say, build between these two rotors, say if I call it a rotor and rotor 2, you can have a gearing action in between them, electrical gearing action in between them, or magnetic gearing action in between them, and you will get two outputs, means outputs at different speed and torque levels. So that is called a magnetic gear. So this is my PhD topic actually. I'm working on this.
On this magnetic gear.
Yeah. Okay. So this question is understood, I think. This one question was remaining from last day's class.
Yeah.
It's an easy question actually. They have in the question itself given the answer. That for the given circuit, the AC voltage across the nodes A and O are controlled by two switches. However, to introduce dead band in the circuit and avoid short circuit due to overlapping of switches of the same leg, the following PWM scheme is preferred. By the course of switching action following the below figure, what is the average voltage across the nodes A and O? So they have given the waveform. So when
VAO is given.
so its average 0. So basically they have written it in this fashion. Yeah, so when Q1 is closed, when your Q1 is closed, then the voltage in you have is 0.5 VDC. And when Q2 is closed, you have minus 0.5 VDC. And when both are open, then you have 0. How can we say it is 0 volt?
Yeah, it is not. It is. We can't say. Real.
Let us say there is a load. Okay, now I have made it even more complicated. We need diode. Okay, forget this. If I consider a resistive load, then we can say VAO is 0, right?
No.
Yes.
Even so, when Q1 and Q2 both are open.
See, when both are open, will there be any current flowing through R?
No.
Then V equals IR. What is voltage?
0. Yeah, I think so, sir. Because if we apply KVL at the top loop, it will become 0.
If it is not
What?
there also, then also it will be 0. I'll tell you why. See, when Q1 and Q2 both are off, that means Q1 and Q2, they are together resisting a voltage of VDC, right? And if I consider them as identical switches, then the voltage across Q1 will be half VDC, voltage across Q2 will be half VDC.
Mm.
Identical switches. Now, if you apply KVL in this loop, so you have increment of half VDC, then decrease of half VDC. So this voltage is 0. So plus half VDC minus half VDC. So this must be 0. We can always say it's 0. Call it a 0.
So in that 0 dead band, they have done that.
I mean, we are trying to find out what happens when both the switches are open. That is 0. Voltage will be 0. Oh, until I lift the pen, you do not get to see what I am drawing.
Ah, yes, sir. Sir, how to make this the triangular wave of 3 numbers?
You already know this.
No, sir. One PWM, I know. One triangular wave.
Hmm.
But
You are
here they are
asking
having
me how
some.
to derive the red and green triangles from the black
Ah,
triangle.
yes. Ah, yes.
Have you not studied summer circuits? I have forgotten the circuit. I have to just make a Google search and find out how it looks. But you have studied this. Sorry. Summer is not our hot summer. This is a circuit that sums.
In digital, we have done some
Why
added.
digital? Analog. You have done this. You have, cannot.
Yeah,
I
three
also cannot
inputs will be.
remember.
Yeah, three voltages
Yes.
will be given op amp. Yes. It
So
will
we
add
have
the
two
voltage
here.
into the.
We have two here. So this thing goes
Yes,
to
yes.
the inverting terminal. Okay, since we are discussing this, let me discuss one thing about it. And there are relations you can easily find out by taking virtual ground and all. So if you have V1, if you have V2, if you have V3, so what you will get is V3 equals V1 plus V2. But you have to take care of two things here. First check that you must do is your V3, say if you are talking about say I have given, let us talk in terms of numbers, okay? So I have given plus 15 volt and minus 15 volt supply to the op-amp, okay? And what you are doing is you are giving, say V1 you are giving a sinusoidal, V2 say you are giving another sinusoidal, say phase shifted. Let us not say phase shifted, say like this. This peak goes to 8 volt, this peak goes to say 9 volt, okay? At the output, what you are expecting, you are expecting this,
17 volts. Yeah.
but you will not get 17 volts. What you will get,
It is
you will
50.
get this. It is saturated, so you have to make sure things are in limit, okay? If you see that your signals are too large, things you cannot keep it in limit, you have to use this circuit. This will make the voltage smaller using the ratio R1 by R2, whatever it comes. You can step down the voltage, then feed it to the adder. So when you are designing the circuit, you have to keep everything in mind and design the control circuit. I'll give you an example that I did, not very complicated one, very simple, but did it some, sorry. So this was this I was doing for my master degree dissertation. I had a machine, a switch reluctance machine, which I had to control. So the current I had to sense. So there was a current sensor like this. So I kept the wire through this. So this is the wire going through the current sensor. You can understand, no? How it
Yeah,
looks?
yes, inside.
Yes. And there are leads. I have given supply to this, and from here I am getting the signal. Now this current source will give you data sheets, their current versus voltage, okay? Now what I would want maximum sweep. Say if the data sheet is say something like this, after some time they will make it like this, I will want full sweep. That is when my machine is, my motor is operating at full load, it should, the controller should be somewhere giving very close to its full voltage. I want this for its sensitivity or somewhere in the sensitive region, right? For this, what I will do, I will maybe give several turns depending on how much current is going and how much is here, that I will give. But the thing is, I was using one TMS 320 microcontroller to control the motor, and TMS 320 can operate only in the zone 0 to 3.3 volt, right? So whatever signal I am getting, I will feed it to the ADC of the TMS 320, but I cannot directly feed it because the voltage level is very high, maybe say 15 volt it is giving. So what I have to do, I have to reduce it. I have to reduce it to this 3.3 level. So I had to feed it to a op-amp, so that at full load current, this output is somewhere say 3 volt or maybe 3.1 or 3.2 volt somewhere. This is there. Now again, op-amp circuits you can directly, since op-amp gives you the power from its power supply, you can directly feed it to the ADC. I do not remember, did I use anything else? Oh yes, I used one more thing, because those TMS 320s were expensive. It took a lot of time to import them, and so I was very careful about those controller boards. So I also put 3.3 Zeners, so that even if there is some problem, it never gets a voltage more than 3.3 volt. Then I fed it to the ADC of the TMS 320. Suppose since you know what SRM unipolar current is enough. Unipolar current is enough in SRM, because the torque is proportional to current squared. So it doesn't matter in which direction the current flows. But there can be other convert machines. Say if you were working on a BLDC, okay, your BLDC, the ideal current should be like this, 120-degree conduction. You have both positive and negative voltage, right? Now how will you feed this thing to this TMS 320? It cannot support negative voltage, it cannot support negative 3.3 volt, or it can only support positive. So in that case, this circuit directly will not work. You will need additional uh, I should not say additional stage. What you have to do is you have to shift this level. So say if you are getting something, you have to shift this level so that this signal now looks like this. Make sure this is inside the 3.3 volt level, then you feed it to the converter, to the controller. Okay, so coming back to your question, how we make this? We make this using summer circuits.
With which they will compare, sir, here? This zero 0.5 will be compared with. Uh,
Hmm?
okay. No, when zero 0.5 is okay. When it is within the band, it will stay at 0. When the zero 0.5 is less than triangular, it will go to negative. Greater than triangular. Okay.
It's not like this. They are directly given to the switch. So we have three, no? The black one, okay, let me draw it this blue. Just a minute. So if this is the black one, say, this is the red one that goes above it, and the green one goes below it. And this is the, just a minute. This is the controller signal. Now you can distinguish the colors, no? So
Yes, sir.
we have two op amps. We have two op amps, say like this. The orange signal, the controller signal, control signal, that goes here and here. One carrier wave goes here, another carrier wave goes here. Then this output goes to Q1, this output goes to Q2.
Okay, the common one is the 0.5, that DC.
Yes, controller, this one. This is the orange one.
So for 1 op amp, uh, the triangle on the top will be given. For other one, triangle on the bottom.
Yes. Now all these
So now,
things you can make your circuit in analog on a PCB or Vero board. Have you ever used Vero board? You should start using these things, if you want to pursue your career in power electronics. Vero boards are, say, if you look it from the top, you will get to see holes in this fashion. Okay, in this way. If you look it from the bottom, you will see these holes are connected through a copper strip. They are connected one line, they are connected another line. In this way, several lines are there. Okay,
like a
they
PCB.
come in,
Okay.
yeah, they come in several shapes and size. This kind of Vero we'll call line Vero. There are dot Veros also. Dot Vero means there will be dots and there will be no lines. There will be simply pads like this. So if you want to say make a, so this is the bottom side, we make the circuit on the top side. In complicated circuit we do many things, but forget that for now. So if you want to connect a capacitor, so you put a capacitor here maybe, so it comes here and the other leg say goes here. Okay, now if you want to connect a resistance in parallel with the capacitor, so that resistance becomes, you shoulder like this, like this, you shoulder them and connect, so they become in parallel. Now suppose one inductor is there somewhere, you want to connect it in series, so you connect it here. What we do sometimes is, if we do not have large space or if you want to reduce the space, we connect the other leg here itself, and with a
Sir, this
knife,
is okay. This is
with a
breadboard,
knife,
they will say. Is it that, sir?
this is Vero board.
Okay.
Breadboard cannot give that much power, it cannot like breadboard. Only breadboard you have 5 connected like this, but here it is many holes connected like this fashion. So and you make a cut here, so that is not connected. Like this way you can make the whole circuit. In line Vero, what you have to do is, in dot Vero, you put the components and then manually short them using shoulders, manually short them using shoulders the way you want. So dot Vero takes a smaller space than a line Vero. Larger the flexibility you have in your hand, smaller your circuit will be, and the largest flexibility you will get from a PCB. These things you will get to buy in electronic shops.
Okay.
Start making, maybe if you want,
Okay.
maybe start what we used to start our journey with, say 15-volt power supply we used to make using these two. With this you used to give a 15 0 minus 15 volt DC supply. This we made, then in another semester we made one square wave generator using op-amp. I think you remember this circuit. I forgot. It was something like this. Something like this it was, I forgot.
Multi-vibrator.
Yes, a stable multi-vibrator. So in the second semester we made this. Then we used to power this circuit using 15 volt plus minus 15. So you get plus minus 15 at the output. In this way we started, then gradually going to other things. Start doing this, make your hands
Okay.
skilled in soldering.
Oh,
Have you done soldering?
yes, sir. Very basic level, but not very
Just
skillful.
keep practicing, keep doing. More things you do, complicated things you do, you have to think of new ideas. You will make mistake. Then after you make mistake, you will learn the technique of desoldering. Then you will learn what problems can happen in desoldering, how to means just this will just increase your experience in all these things. Okay.
The robots. This is the first time I'm hearing, sir. No one told me.
Then why did you solder?
Sir,
You said
in
you did
P-
soldering.
yeah, in PCBs we do, but these things
Okay,
look
PCBs
different.
is PCBs costly. No, you have to first design the PCB. Then you have to make the Gerber file out of it.
Mm.
You have to send the Gerber file to a company. They will make it. They will charge you a lot if you are making
Yes.
one or two.
Yeah.
But wherever you will get, I do not remember, but I think 4 5 years back I used to, no, not that long also, 3 4 years back I used to buy. I forgot the numbers. There was one, say, I guess it was around 10 centimeter by 8 centimeter, something like that. It was around 15 or 30 rupees, something like that. It was, we used to buy components, then soldered them on the Vero board. Nice thing. Vero boards, if you keep for long in the shelf, the coppers will lose the gloss. Then you have to rub the surface with very thin sandpapers.
Mm. Yes.
Start doing
In
these
the
things, you will get to see many things. Yeah.
in this, if I suppose want to give plus 15 volt into this board,
Hmm.
uh, how to give that, sir? This do they have to peg some pins here?
Yes, those things are available.
Okay.
Uh, they would look like this. Let me draw. Yeah. They would look like this. You can imagine how it looks like. So from
Ah.
here, if you see, there will be two holes, and here there will be screws. So we will
Oh, that.
put in wires and screw them,
Yes.
and there will be pins and
This
everything. Yeah.
they'll call terminal block.
Hmm. We used to say connectors, whatever. All these distances, distance between two rails, distance between two holes, these all are standard. You will
Oh,
see that this block will exactly go into it.
fit into it.
It may so happen that the hole is so small it doesn't go into. You have to drill it a bit, but measurement wise, it will directly go into it.
Mm.
I used to remember all these dimensions when I used to design PC. Forgot. There are standard dimensions you can see, 1.5 inch or something. If you make hardware in your your BTech dissertation will automatically become one of among the top 1% in this country. Okay, anything else? So I hope this course, I don't know how you enjoyed this.
So it's
I enjoyed specifically, as you have understood by now, that my area of expertise is not not the device. I'm not saying I'm expert in converter also, but as power electronics engineer, I am mostly concerned in this converters. There are specialized engineers now who are doing research on GAN, SIC. They are interested in device again, but I am mostly interested in converter. We try to study converters in the most general way possible. That is why I took up this circuit today.
yes, sir.
You should be able to analyze any circuit given to you in this fashion. Just, it does not matter how many inductors, how many switches are there. Simply keep on drawing the circuits in different modes, and then keep writing the voltage across the inductors, then apply the theorems. You will get all the relations. It is that easy. Good that we could discuss some practical things. I do not have photos, like I used to click photos of these circuits, but I have lost all of them. 2016 I made my first circuit. This was 7815 and all.
Oh,
Okay, since everything is done, let me tell you one out of context irrelevant thing if you do not have any more question.
yes, sir.
This is not irrelevant, this is very much relevant, but out of context to some extent. That is, I will tell you about one of the softwares that I like a lot. Again, a free software. I how do they like write it? You might have heard about it though.
LaTeX.
Yeah. Do you use LaTeX?
No, sir. Some workshops happened in my college.
Start using LaTeX. Okay. I will strongly recommend you to do so. See, LaTeX, what happens is you can make your document, you can make your presentation, you can make posters. Not only that, these are the kind of documents that you can make. And apart from that, what we also make in LaTeX are plots, drawings. When I mean drawing, I say drawing, I mean engineering drawing, as well as circuits.
Oh, you can draw circuits also.
Yes, you can draw circuit. I will give you one link. Just a minute. This is a tutorial on how to draw circuit in LaTeX. So many things you can do in LaTeX. So right now what we do is we do not even go out of LaTeX. We try to do our works as much as we can do. This term you can keep in your mind. I don't know if you have heard of it. Vector graphics. So whatever drawings you make using LaTeX are all vector graphics. Since this thing came, I will tell you about another software. Again, free software, Inkscape. Very powerful software. You can use it for your technical drawings. It also makes all vector graphics, and at the end you will get very wonderful outputs, and not only wonderful, very professional looking outputs. So I would recommend you to use these things extensively.
So this vector graphics is a format, right? Format
Is
of.
a kind of format. Vector graphics formats include SVG, EPS, PDF. Vector graphics means, see, SVG is scalable vector graphics. EPS is encapsulated PostScript. PDF, portable document format. It means, see, look at this name, scalable vector graphics. You draw something, then you can scale it in as large as possible. It will never be pixelated, because vector graphics does not say, when you draw a straight line, what it does is it takes information. At this pixel it is like this, at this pixel it is like this, in this way it takes information. But vector graphics doesn't keep it like that. Vector graphics, what it does is like a vector. It has defined this point, say, as alpha beta, this point as, say, gamma delta, and it will tell that between alpha beta and gamma delta there is a segment whose properties are this, thickness is this, color is this, all the information it will save. So in this fashion, even if you zoom in, these informations are used to generate the picture there, so it never cracks in that way.
Yeah, our JPG images beyond a certain zoom, it will break.
Yes.
Is it latex is a free software?
Yes, it is a free software. LaTeX you will not directly get. What you have to download is Mictech. This includes all the library that you need. You can download other libraries also, and you have to, there are several softwares. I use TextStudio. There is a TechMaker also. This TextStudio is where you will write your code, and Mictech will run in the background. So TextStudio will run above Mictech to create the document.
Which side is better to download this free software?
Just search for Mictech download in Google.
Mictech.
Yes.
There comes many sites which are offering
First
Mictech.
one. Okay, I will send you. First one, get Mictech. Mictech.org. Okay, since we are, let me show you some documents that I made with Mictech and LaTeX. Papers and all we all write, but I cannot show you papers directly right now. I'll show you some things. What to show? Okay, I will show you this. Wait. See, these diagrams are all made using LaTeX by writing code on LaTeX. These circuit diagrams. This thing. This kind of,
Connections, everything.
yes, sorry.
No, these connections, everything we can write in a code itself.
Yes, yes. It looks very professional. The next things I cannot show you, they are my PhD works, not unpublished. one last thing I will show you, then we will call it a day. What happened?
Sir, in that channel, if we have some query, can we ask in there?
I think yes, but it depends on the whether he will answer.
Sir, how is it different from the circuit generated by LT Spice or P Spice?
See, LT-Spice, you are drawing the circuits to simulate, but here we are drawing the circuit to present it in our document, in our report, in our presentation. So you can draw it in LT-Spice and take a screenshot, but it looks very unprofessional. You will never see such things in papers.
Okay, okay.
Okay, then we'll call it a day and end of the session. I do not see others present today, but specifically Raja, I would like to thank for asking questions throughout the session and making this session possible, because 2 hour session without questions from you is very difficult. And Mr. Rakesh also, we have asked several questions in the last few classes. I'd like to thank Shanti, Mr. Devkar, one TD, I don't know what his name is. They used to join and ask questions. So thanks for your questions. Helped me a lot in learning and making these sessions possible. We will wish you all the best for your future endeavors. Thank you.
Thank you, sir.
For the past 2 months, you have enriched us as many of the knowledge. We have gained many things from you. You have patiently answered us. Thank you so much. This knowledge will be with us for our lifetime.
Okay. Thank you. That's very enlightening.
Sir, thank you,
Yeah.
sir, for sharing your practical knowledge also, apart from this academic this thing.
Thank you. Thank you very much. Goodbye. Then I will call the.
Thank you, sir. All the best for your PhD, sir.
Thank you.
Yeah, best
All
of
the
luck,
best
sir.
to you too. Thank you.
Thank you.
Thank you, sir.